focus on limiting reactants today. I did part 2 on last week after my coughing session. I think I've narrowed it down to allergies because when I take an antihistamine, my cough gets significantly better. So I think it's down to allergies. Okay, all right, so let's jump over to here. All right. Okay, the deal is, we've always talked about stoichiometry having 4 steps. And if there's a reaction, you balance it. You look at for what's given, what's to be calculated. Then you do the setup. It's in 3 parts. Okay, however, if there's an extra reactant, multiple reactants, then you still need to figure out what's to be calculated. But then the setup is different because you need to figure out which of the multiple reactants is limiting the amount of product. Okay, so, and that's usually a 2-step process. So basically what you do is you assume that each reactant produces product and see which is less. And then frequently, the problem will ask what's left over reactant-wise, and that's another 2 more steps. So instead of 1-step setup, like here, it's a 4-step process. Now, I mentioned this last time, but if we start with a big pile of bicycle tires, a pile of handlebars, frames, and seats, how many bicycles can we produce? Now, if you think of these guys here, the bicycle tires, handlebars, and frames as being the reactants, and the actual bicycles themselves being the products, then what we can do is go through an analysis and figure out if we have 10 bicycle tires, how many bikes can that produce? 5, because it takes 2 tires per bike. If we have 4 handlebars, now this is exclusive of anything else. If we have 4 handlebars, we can produce 4 bikes because there's 1 handlebar per bike. Same with frames. We have 3 frames. There's 1 frame per bike, so we can end up with 3 bikes. If we have 6 seats, 6 bikes. So what's limiting in this pile of bicycle parts, what's limiting the number of bikes is how many frames we have, because it produces the least amount of bikes. Okay, so this process here is what I'm talking about here. Is this right here. Okay, so let's look at a reaction. Okay, if we have a piece of iron and it's exposed to oxygen gas, we are going to produce ferric oxide, which is also known as rust. Okay, so the question is, how much rust can we make? We start with 15 grams of oxygen gas and 12 grams of iron. And then how much excess reactant is left over? And if only 1.3 grams of rust is produced, what's the yield of the reaction? Okay, now this is a typical limiting reactant problem. Very typical. We have 2 givens. 2 givens. That means we have to figure out which of the givens produces the least amount of rust. That's our first job. That means we have to consider the iron separately from the oxygen gas. Okay, so step number 1 is balance the equation. Is the equation balanced? No, it is not. Let's see, we have 2 irons here, 2 irons there. We have 3 oxygens here, If we have 3 halves there, will give us 3 oxygens. Okay, so okay, we need to clear the fractions. That means multiply everything by 2. So that's going to make this 4, that 3, and that 2. Okay. So let's start with the oxygen gas first. Okay, so we're going to have O2. Excuse me. And we have 15 grams of oxygen gas. Now, we want to know how much rust is produced if we start with 15 grams of oxygen gas. We don't care about how much iron there is. That's the next step. We're just looking at the oxygen gas by itself. Okay, so that's a 3-step process. First step is convert the grams to moles. And oxygen is 16 grams a piece, so that's 32 grams per mole of oxygen gas. Okay, the next step is from the balanced equation. Okay, and we need to have the oxygen on the bottom so it cancels. And we're producing rust on the top. And that from the balanced equation is going to be 2 to 3. And then we need to go moles back to grams for rust. Okay, so what is the molar mass for rust here? Oh, I need a periodic table. Let me grab this periodic table right here from last time. Okay, so we need 2 irons, and iron is 55.85 a piece. We need 3 oxygens, and those are 16 a piece. So we have 2 irons at 55.85 a piece, plus 3 oxygens at 16 a piece. So we're looking at 159. So grams per mole. Okay, so that's going to go here. So we've got grams cancel, moles cancel, gives us grams of rust. Okay, and what is that going to be? 15 times 2 times 159, 7 divided by 32 divided by 3. Looking at 49, 9. Okay, so that's if we just look at oxygen. Now let's do the same process, only instead of oxygen, we're going to start with iron. And how many grams am I? 12. Okay, so we have 12 grams of iron. Remember, iron was 5585. OneNote is not responding. I'm going to have to I'm going to restart OneNote here. Can you guys see the screen?
Yes.
Okay. Okay, so that gives us grams to moles. Next one is balanced equation. We want the iron to cancel. We want rust on the top. And from the balanced equation, that's going to be iron is going to be 2, and rust is going to, excuse me, iron is going to be 4, and rust is going to be 2. So this way we have grams cancel, iron cancel. Next, we need to convert the moles to grams. Okay, let's see how much rust is produced if we're just looking at 12 grams of iron isolated. We're looking at 17.2 grams. 366. Okay, so the iron is definitely the limiting reagent because it's smaller than the oxygen one, okay? So we've determined now that the iron is the limiting reactant. It limits the amount of rust we can make. Does everyone see that? That means we have excess oxygen left over. So what we're going to do is we need more room. So I need to do a little cut and pasting here. Okay, so now we know we're going to make, we know we're going to make 17 grams of rust, no more than that. because the amount of iron we have isn't enough to make more. So we're going to have excess oxygen. So now we need to figure out, okay, if we have excess oxygen, how much oxygen are we going to use if we make 17.2 grams of iron? Okay. And there's two approaches on this, but the easiest way, if we start with the 12 grams of iron, okay, if we start with 12 grams of iron, how much oxygen is that iron going to need to totally burn up? Okay. That means now we're looking for grams of oxygen. Okay. And this comes from the balanced equation. So we're looking at 4 to 3. And oxygen is 32 grams per mole. Grams cancel, moles cancel, iron cancel. So we're left with grams of oxygen. So let's see how much oxygen is consumed when we totally burn up or use up all the iron. So we're going 12 times 3 times 32 divided by 55, 8 divided by 4. So we're going to use up So we're going to use up 5.16 grams of the oxygen burning 12 grams of iron. That means we have leftover oxygen. Okay. And how much do we have left over? Well, we started with 15 grams. And we used 516. So how much is that left over? Well, that's 84. Yeah. Okay. And then if we only made 1.3 grams of rust, what is the yield? Well, the theoretical yield is 17.2 grams. That's with everything going perfectly. And of course, it never goes perfectly. You get all kinds of stuff going on. You know, your glassware could be dirty, or conditions could not be perfect and optimal, blah, 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 whatever reason. Okay, so theoretically, the most we can get out of these conditions is 17.2 grams. But we only got 1.3. So our actual yield is 1.3. And we had what, 17.2 theoretical times 100 to convert it to percent. That gives us what? So a little under 8% yield. So this is a typical limiting reactant problem. Okay, so there's quite a few parts. That's why I was stressing before to go through when you only have a single reactant, because it's less calculations. Okay, so any questions about any of this? I'm going to do another example here in a second.
No questions for me. Thank you.
How's your sinus infection?
You know, getting better. Thank you for asking.
I've got allergies. That's, you know, I'm just hoping that mine doesn't go into an infection because I hate sinus infections. Oh, anyway, so I'm glad you're feeling better.
Thank you.
Okay, so let's do another one. All right, so when propane burns in your barbecue, this is the reaction. Propane is a 3-carbon hydrocarbon, and this is what it looks like. C3H8 burning in your barbecue, so it requires oxygen gas, and it produces carbon dioxide and water. Now this is assuming your jets are properly adjusted. If your jets are not properly adjusted and you get a lot of yellow flame, you're going to get black on the bottom of your pots or your meat or your vegetables. That's not the same black as you get when you put a char on your meat or vegetables. That carbon is coming from the meat or vegetables, not from the propane. So there's 2 sources of carbon whenever you barbecue, from the fuel and then from your food. Both produce carbon black. Okay, so this is a reaction. And is it balanced? Well, let's see. Okay, so we have 3 carbons, 3 carbons. We have 8 hydrogens, and we have 8 hydrogens. Okay, and we have 2 oxygens, and we have 6, and 4 is 10. So if we put a 5 here, that'll give us 10 oxygens. So it's balanced now. Okay, so if we start with 34.5 grams of propane and 23.7 grams of oxygen gas, how much water do we produce? Okay, how much water do we produce? Well, since I've given you 2 givens, that requires 2 calculations to determine which will produce the least amount of water, the product. Okay, so let's do propane first. And the first step is always convert the grams to moles. Okay, so 3 carbons at 1201 apiece, 8 hydrogens at 101 apiece. Let's see what that adds up to be. Let's see, 3, 12, 1 plus 8. And that's 44, 11 grams per mole. Okay, next step is to convert the, what is wrong with the setup I just did, by the way? What do I always have to do in the first step? oops. You have to, remember the grams have got to cancel. Are these going to cancel?
No, the grams can't cancel on that.
Right, so I need to flip it. There. Okay, so that's the grams to moles. Our next step is from the balanced equation. We want propane on the bottom and we want water on top. Okay, so from the balanced equation, we're looking at water's 4, propane's 1. And then the next step here is going to be moles of water, grams of water. Okay, and water is oxygen, 2 hydrogen, so that's 16. And 2 waters is 2 hydrogens is 2O2. That's 1802 grams per mole. Okay, let's see, we got all cancellations here. Leaves us with grams of water. That's what we want to calculate. Okay, so let's grind this baby out. Okay, so that gives us 56 grams of water. Okay, now let's see what 23 grams of oxygen will give us water-wise. Okay, so it's 23.7. Yeah, 23.7. In oxygen, it's 32 grams per mole. And then from the balanced equation, we want oxygen on the bottom, water on top. Water's 4, oxygen is 5. And oxygen and water from up above is 1802. Okay, so we have grams cancel, moles cancel, oxygen cancel gives us grams of water, which we want to calculate. Okay, so just from oxygen, we're getting 10.7 grams. And then from the propane, we're getting 56.4. So oxygen is clearly limiting the amount of water produced. Okay, now what's the yield? Well, yield is what, 456 of water. The theoretical yield is 10. We have 456 by 10, 7. Gives us what, 40.6% yield. And then how much excess reactant do we have? Well, we have a whole bunch of propane left over. So how much propane is needed if we burn up all the oxygen? Okay, we're using up 23.7 grams of oxygen. We want to know how much propane are we going to use up if we burn up all the 23.7 grams of oxygen? Okay, so that ratio, see, we want propane to oxygen, going to be 5:1. And the propane, we already did the molar mass for that, it's 4411. And let's see how much propane we've used now. So grams cancel, oxygen cancels, moles cancel, gives us grams of propane used. So that's 23. Okay, so we've used up 6.533 grams of propane. We started with 34.5 grams. Okay, so we're looking at 97, what is that? So 27.97 grams excess propane. Okay. Okay. So those are two detailed examples of limiting reactants. What happens when you have more than one starting material? Okay, step number one is we need to find out which of the reactants limits the reaction. Now, if you have two givens, that's 2 steps. If you have 3 givens, that's 3 steps. You have to run each one through independently. Whatever's less limits the product. The next step is to find out how much you have left over of the other one. And that's a two-step process as well. Now, this is reality in a modern production facility. A friend of mine ran a Union Carbide chemical plant making pesticides. So he had boxcar after boxcar full of reactants coming in, and he had boxcar versus boxcar of products leaving. And his chemical engineers had to make sure that they didn't waste excess reactants. So they had to be very careful on not having a lot of excess there. If the excess was there for a reason, that was different. But if they didn't want to waste reactants, they had to gauge this so that they were both used up together. That's why multiple step reactants problems, stoichiometry problems, are important to do. Now, this problem, for those who are taking 400 next semester, you will have a quiz week 1 of some stoichiometry problems and some naming problems. So if you're going into Chem 400 next semester, Unit 5 is a really important unit for you, as well as the naming unit as well. But particularly stoichiometry. A higher percentage of topics in first semester 400 is stoichiometry. So if you can do these, you will be well prepared for success in Chem 400. Okay, so that's what I wanted to cover today. I'll put a quiz together for you that should be available hopefully by tomorrow night. We're not going to do anything more this week since we're coming into Thanksgiving. But do the extra problems I gave you as practice. I'll give you lots of practice. Okay, how are you guys doing?
Doing okay, just, need more practice like usual.
Yeah. But you're able to follow the steps?
Yeah, and if I just think about it as putting together 2 of the problems we were doing before, and like it makes it feel more manageable to break it down into the parts instead of, it feels more overwhelming when I think of it as one problem.
Yeah, well, I mean, look at look at all the parts. Oops. I mean, there's a lot of parts, and so yeah. Hopefully, excuse me. Hopefully, this process here, where I gave you the individual steps to kind of break it down. When you read the problem, it doesn't seem all that hard, but then really there's a lot of steps to it. So, okay, well, please practice. Next week we're going into let's see, there'll be no math in chapter 12, but in chapter 14 there will be a fair amount of math again. We're doing getting into liquids, solids, intermolecular forces, and solutions. Solutions is where the mathy comes back in concentration. Okay, so anyway, go ahead and practice these. Feel free to shoot me emails on questions, making sure I did my math right. Hopefully I did. Okay, and Sally, that email I sent you regarding your question about turning the lab in today, did that make sense?
It did. Thank you so much. I appreciate your help.
Okay, good. Okay.